How would we go about parallelizing a modern application, one we'd like to see run faster? When we say modern, we mean one that is modular, that is, whose internal structure is a modular design. Modular design, such as Model View Controller, has been in practice since at least the 1980s, and is a good idea regardless of parallel computing. If an application is modular, this means that it can be organized into components that are either its front end or its back end. The front end is code that supports the application's user interface, basic data input, presentation of output, and other high-level functions. Particularly, we mean the functions that control the overall execution of the code. The back end has the code that does the real work, such as the fundamental calculations or data processing of the application. We refer to the low-level grunt work of the application that helps define the application's purpose. In the Model View Controller parlance, the view would reside in the front end, and the model lives in the back end, while the controller may be split between the front end and back end depending on the specifics. When the application normally runs, it accepts instructions and parameter data, ultimately from the user, via its front end, which the front end then supplies to the back end, which processes that data. When those results, or end results, are ready, the back end supplies that as data back to the front end for display for the user or other means of output. To parallelize this modular application, we split the front end and back end apart and get in between the front end and back end with our supercomputing engine technology, or SET. We then replicate the application's back end, one for each computing core or processing element, on the multi-core computer or cluster or supercomputer. Each of these application back ends are running independently other than the connection to SET, and they're essentially unaware they are running in parallel. So to the front end, SET looks like the back end, and to the back end, SET looks like the front end. We can show you how SET is structured. SET is actually separated into pieces, one for each application's back end. Internally, SET uses all-to-all communications, just like modern supercomputers, to support the computation of the application on the parallel machine. When the SET parallelized application runs, the application front end supplies instructions and parameter data as before, but then SET takes those instructions and data and spreads them out to make them available to all the application back ends. The application back ends each perform their calculation, but depending on the application there may need to be some communication, which SET provides to support the calculation. When the results are finished, SET can help stitch the answer together for the front end to display for the user. The SET API supports numerous tasks inside the parallelized application. SET organizes and manages both data and arrays held in the application across the parallel system. This data is available to the application at any time, but to support parallel computing and communication, it is necessary for SET to know about the internal structure of this data. SET also organizes the execution of application code on the cluster. This execution is entirely under the control of the application front end, like the captain of a ship, but SET handles the details. Following that, SET supports collective communication including traditional MPI patterns like broadcast, gather, and scatter. But because SET knows about the data structures, unlike MPI, it can handle parallel execution and its output, such as divide and conquer scenarios. Many computations require maintenance of boundary conditions between, or elements residing in, parts of a large array partitioned on the cluster, so SET helps manage guard cells and element membership between partitions. Like execution, these data movement patterns are entirely under control of the application front end as well. This is how we see the landscape of parallel computing paradigms, and we see that SET has important advantages. Running an application in the context of sequential and traditional desktop computing is always the first milestone in an application's development. It's clearly lower cost than any parallel computing, and many applications today stop there, but it's also the slowest. Multicore can sometimes enhance speed, benefiting from operating systems being multicore aware, but the benefits of multicore by itself are very limited for the typical software industry writer. With considerable additional development cost, grid and multi-threading approaches can give better performance, but their efficiency is less than is possible using modern supercomputing techniques. The computing paradigm of MPI is the ultimate supercomputing approach. but it comes at a substantial price, in that you need to hire elite expertise to achieve the ultimate in performance. GPU hardware can also achieve spectacular results, but GPUs are very finicky in how data flows in and out of GPUs, so its performance is fragile, which translates into a lot of trial and error and or expertise for the GPU software writer. The line from sequential to MPI and GPU defines the traditional performance programming barrier, a compromise between performance and the cost of code development. SET, because it internally adopts the parallel paradigm of MPI, can achieve nearly the performance of MPI, but it allows the software writer to think largely sequentially. This makes parallel computing accessible to a much wider pool of software programmers, rather than restrict parallel computing to the elite. Hence, SET breaks through the performance programming barrier and makes it possible for applications to become parallelized far more quickly and inexpensively than before.